In Chapter 9, we're only going to talk about two sections. Section 9.1, which is all about polar coordinates, and Section 9.2, which is about polar equations and their graphs. The reason we're going to study this is because it's really helpful in calculus, because there will be, when you get to Calculus 2, there will be lots of problems involving a coordinate system that is not rectangular. So it doesn't have an x and a y axis, and rectangular coordinates where little squares. Instead, it's something that's called a polar grid. Okay, and so it's another way to talk about things that have coordinates or locations on a graph. So the idea is that there's a center, which is called the pole or the center. Around that center are circles, and these numbers here, the 1, the 2, the 3, and the 4, those each represent the radius of that circle. So this is 1 unit, and then 2 units, 3 and 4 units. And then there's all these lines coming out. There's actually an infinite number of these lines going through the center, and they sit at angles from the horizontal, which is 0. And so those represent degrees, just like we've talked about in the trig. But that's instead of the two xy, you end up getting a radius and an angle. So your coordinates are of the form r theta, right? Where r is the radius of the circle that the point is on, right? Or think of it as the distance from the pole. And then the theta is the angle, right? And so let's take a look at some points. So for instance, if I had a point here, right, its coordinates would be 3 because it's 3 units from the center, and then pi over 2 because that's where its angle is. Yeah. We might have something right here which is like 3, 0 because the angle is 0. Notice that that coincides with the same 3, 0 that's on the regular coordinate plane, rectangular coordinate planes. And we would also have, if we had something over here, we do call it -3, 0. Even though really it is, okay, I'm not sure when that stopped recording. But we have points 3, 0, that's right here, that is the radius 3 at 0 angle. And then we also do have points with negative x coordinates. Here we'd have -3, 0. All right. Some other points, you might have something like 3 or 4, let's say, 4 pi over 3. So that's, somewhere here the angle 4 pi over 3 is going to be between 5 pi over 4 and 3 pi over 2. So 4 pi over 3 and so on. Okay? Why do we have this? Well, it can be easier for some applications in calculus to think of equations or functions in terms of polar coordinates instead of x and y. Okay? All right. So what we're going to do is we are going to work on converting polar to rectangular coordinates and back again. Yeah. And there's something that's going to help us quite a bit. Whoops. There are a number of things that can help us with this, but the main thing that helps us is this idea that if we have a point, so we have P as a point with polar coordinates r, theta, then we can transform the r and the theta into rectangular coordinates, which are the ones we're used to, the x, y's. So it's rectangular coordinates x, y are x equals r cosine theta and y equals, pardon me, r sine theta, right? Or if you think about them, you know, in terms of a point, they would be r cosine theta comma r sine theta, right? So you might be saying, where does this come from? Well, let's recall something. Remember when we were first learning trig and we said that sine theta is equal to y over r, right? And that's for some, and cosine theta was x over r. That's for some angle theta in standard position whose terminal side intersected with the circle of radius r, right? Instead of a circle with radius 1, the unit circle, we had a radius r, right? And that point xy where that intersected, you know, we would definitely say was the cosine theta comma sine theta, yeah, x over r and y over r, right? So notice these, if you just multiply both sides, you know, both sides of here by r and both sides of here by r, you get r sine theta equals y and r cosine theta equals x, which is just what we have right above, right? Why is this made this way? Well, remember the unit circle, right? The unit circle is drawn on a rectangular grid, right, with rectangular coordinates. Remember, the unit circle is the circle with radius 1 that's centered at the origin. So we have all these points, 1, 0, 0, 1, negative 1, 0, and 0, negative 1, right? And then let's say we had some angle in standard position, and let's say it's pi over 4, right? This point xy right here, where the terminal side intersects the unit circle, we know that the x-coordinate is the cosine of pi over 4, and the y-coordinate is sine of pi over 4, right? We also know that those values are square root of 2 over 2 comma square root of 2 over 2, right? So if we think that we know that the unit circle has radius equal to 1, right? Cosine pi over 4 is the same thing as 1 times cosine pi over 4, and sine pi over 4 is the same thing as 1 times sine pi over 4, right? The cosine pi over 4 is the x, and the sine pi over 4, 1 sine pi over 4 is the y, right? So we see again this idea that x is equal to r cosine of theta, and y is equal to r sine of theta that we defined above. It's just that here our r was a 1. Okay? All right, so it's a way to think about all of, you know, a different coordinate system based on the idea of the unit circle, which actually does happen on a rectangular grid, but then the, you know, the grid is changed to a circular, or what we call the polar grid. Okay? All right. So we're going to work, I'm going to do a couple of examples. We're going to convert negative 2 comma 2 pi over 3 that's in polar coordinates to rectangular coordinates. Okay? All right. So looking at this point, I know that r is negative 2 and that theta is 2 pi over 3. Okay, so the first thing we're going to do is think about where this point is. Okay, so I know that I've got radius 2, right, and theta is 2 pi over 3. So let's think about where 2 pi over 3 is. Well, pi here would be 3 pi over 3. So 2 pi over 3 is this angle right here, right? And our radius is a length of 2. And it's actually negative 2. And so that means this is 2 pi over 3. And so this is here in quadrant. No, it isn't. Let me take it back. Whenever we see a negative in the r, right? Sorry. Whenever we see a negative in the r, it means that you take the angle. So this angle here that I just drew would be 2 pi over 3. But the one that would continue if I drew a continual line right here is actually going to be -2 and 2 pi over 3. So we can see that this is happening in quadrant 4. So that's what the negative means. -2 kind of tells you, I like to think of it as kind of telling you which way you're going on the, you know, like which way you're going around. But it's always across, so you treat it like it's +2, and then you extend the line and go to that angle. Okay, so we're at quadrant 4 here. All right, so let's use the conversion factors that we have above. X is equal to r cosine of theta, and y is equal to r sine of theta, and we're going to plug in what we know. Well, our x coordinate will be -2, because that's r cosine of 2 pi over 3, and our y will be -2 sine of 2 pi over 3. Okay? So x is going to be -2, the cosine of 2 pi over 3 is -1/2, and here for y we're going to have -2 times the sine of 2 pi over 3, which is square root of 3 over 2. Okay, now let's evaluate these. So x is 1, right? And y is -√3. So then we say that our polar coordinate, our point with polar coordinates -2, 2 pi over 3, we're going to say it's the same thing as 1, square root of 3 in rectangular coordinates. Now be careful. Sometimes people get a little bit confused with this. So the reason that we graph the point is to figure out what quadrant that it's in. And quadrant is helpful for us because when we come up with our final point, we see that, oh, this point would be in quadrant 4 also. But be really, really careful. When you're filling in the cosine and the sine values for this 2 pi over 3, you use actual 2 pi over 3, even though you wouldn't really think that this angle right here is 2 pi over 3. Does that make sense? Sorry, my kids keep coming in and out. But again, so you graph it to make sure you're getting in the right quadrant, but you use the original value of theta to plug in, you know, into your cosine and sine. That way you get the correct SIGN sign here and here. Okay, we're going to do another problem. We're going to go the other way. We're going to convert -3, 3 to polar coordinates. Oops, not polar coordinates. Now, where is -3, 3, right? -3, 3 in rectangular coordinates is here. So it's in quadrant 2. Okay, so that's important to note. Okay. Now we could use the x equals r cosine theta and y equals r sine theta and make a system of equations, but there's actually an easier way that also leads us to a few important identities that might help us later. Okay, so remember what we're looking for. So I'm going to go that way. We need to find r theta, right? So let's first work on r. R equals what? Well, if you take a look at our graph and you think about the distance between the origin and our point, we could call that r. We know that this distance here is 3, and this distance here is 3, but I'm going to call it -3 because it's in the negative direction. Okay, so if I were to look for the distance of r, I could use the Pythagorean theorem, and I could say, oh, r squared is equal to -3 squared plus 3 squared. Notice that -3 is going to get squared, so it doesn't really matter if I use the positive or the negative to begin with. So that means that r squared is going to be 9 plus 9, which is 18, and that r is the square root of 18, or 3 times the square root of 2. Okay, so that's the distance from the origin to the point, and that's my r. All right, I want you to notice something. Basically, we did r squared equals x squared plus y squared, right? That is very important, and we're going to be able to use that. It's a truism. It's always true. It's an identity. Okay, and we're going to be able to use it in a future problem. Okay, next time.